So, hi everyone. Thanks for joining this talk of the AFMS seminar series today. Today, Associate Professor Danielle Moreau from UNSW Mechanical Engineering is talking about aeroacoustics. So her research focuses in the field of experimental aeroacoustics and also production and control of flow-induced noises. And today she's going to talk about flow noise sources of rotating blades. So thank you so much, Danielle, for accepting our invitation, and we're looking forward to hear more about your work.
Thanks so much, Azadar. Yeah, thank you all for joining today. It's great to be able to share with you what we're currently working on in the Flow Noise group. So this talk is going to focus on two aspects of our current work, looking at flow noise sources of rotating blades. So if you're not familiar with flow-induced noise, what I'm referring to here is a noise that's produced due to turbulent flow interacting with a solid surface. And it can be a dominant noise source for many different types of technologies. So for air, road, rail, underwater vehicles, cooling fans, wind turbines, they all produce flow-induced noise. And it's particularly problematic for things like UAVs. There's growing use of UAVs and an emergence of urban air mobility technologies. And this means that flow-induced noise, really has to be considered from a design perspective. And it's also a regulatory challenge as well for these technologies. And you can see that in many of the examples that we've got on the screen here, the flow-induced noise sources are the rotating blades. Wind turbines, cooling fans, UAVs, and urban air mobility vehicles, they all have a rotating blade system. And that's what I'm going to focus on today, is some of our current work on understanding the mechanisms behind the flow-induced noise produced by rotating systems. So a little bit of a general background to how we study flow-induced noise. I typically perform experiments. This is what we do in our group a lot. We perform experiments in a specialised wind tunnel facility that we can basically acquire simultaneous acoustic data with flow or aerodynamic data. And this is our anechoic wind tunnel at UNSW. So it's a suction tunnel, and it produces a maximum flow speed of around about 60 meters per second over this outlet here. And that allows us to achieve Reynolds numbers above 1 million for an airfoil with a chord of about 0.3 meters. So the facility is driven by this fan here, which is at the downstream end of the facility. And that connects to an anechoic chamber here through this acoustically lined U-shaped duct. And this serves as a diffuser to expand the flow and also as a muffler to attenuate the fan noise and prevent it from entering the test section. So the air enters the facility through this flow conditioner here, and then it's accelerated through the contraction into the anechoic chamber. And we mount our models here at the contraction outlet, typically between two plates. And the inside of the chamber, it's acoustically treated with thick foam to create an anechoic environment above about 300 hertz. So this is the facility that we use for our experiments. And in terms of what we measure, to study flow-induced noise, we take simultaneous measurements of the far-field noise, the unsteady surface pressure, so that's the surface pressure on the object itself in the flow, and flow field measurements. So we try to study the full chain of causality from the turbulent velocity fluctuations to the unsteady pressure that it produces on the surface to the far-field noise radiation. And that allows us to understand how the noise is created. So to measure far-field noise, we use a microphone array. So this is a look inside our anechoic wind tunnel. So you can see the foam-lined walls. We've got the outlet here, and we've got a model mounted between two plates. And we've got a jet catcher here to contain the flow. And we use a microphone array, you can see it in the background here, to measure the radiated sound from the model in the flow. And we use the acoustic beamforming technique. And that's essentially like an acoustic camera. And it allows us to almost take a photograph of the sound and understand where on the model is the sound being created for different frequencies. So our microphone array here, so each of these black dots is the microphones. Our array in this example has 64 microphones in a 9-arm spiral. And in another example inside our tunnel, we can also perform 3-dimensional beamforming of 3-dimensional noise sources using 3 planar arrays as well. So that's typically how we measure the sound that's radiated, by using an array that's located outside the flow. And then we also use several different methods to measure the flow. So we have several PIV systems. You can see a camera and a laser arm in the photo. And we also use hot wire anemometry and pitot probes and things like that to analyze the flow. But a very important technique for us is measurement of the fluctuating surface pressure. And that's really instrumental to identifying the aeroacoustic sources. So the sources of sound, we're essentially measuring the noise sources by measuring the fluctuating pressure. So to measure the fluctuating pressure on the surface, we use what's called the remote microphone technique. And with that technique, we use very small holes or taps in the surface of the model. And we connect those taps to hollow channels that run through the model. And then to that, we connect plastic tubing. And then we route the plastic tubing to a microphone housing like this one here that allows us to measure the pressure fluctuations that pass through the tap, down the tubing via a microphone. So one thing I will mention as well is that this housing contains this anechoic termination, which is a really long, 3-meter long plastic tubing. This stops reflections of the surface pressure fluctuations from returning back into the housing, so that we get an accurate measurement of the surface pressure at that pressure tap via this remotely located microphone. So an example of this setup you can see in the first photo here. We have a model with a 3D printed sort of insert section. You can see that down here. And the pressure taps are the small holes that you can see along the cord and also at the leading edge here. So we connect plastic tubing to the bottom of these open channels, and then the plastic tubing runs through the rest of the model below the plate and then connects to these microphones, these remote microphones sitting below the plate. So that allows us to measure the surface pressure, the fluctuating surface pressure with these microphones. And you can see an example of a finite wing model here. You can see all of the channels printed into the model. And another important part of this technique is calibration. So we need to account for the fact that the pressure signal passes through these channels to the microphone. And to do that, we use a custom calibration method here. So we have this calibrator that consists of a loudspeaker that's placed at the back of this sealed cavity. And during the calibration process, what we do is we basically press the opening of this cavity over the pressure tap, and then we record the signal from the loudspeaker with the remote microphone and another reference microphone, which you can see in the image here, which is very closely located to the pressure tap. And then we calculate the transfer function between the reference and the remote microphone, and then we apply it to the remote microphone signal to account for the the fact that that pressure signal has to pass through those channels in order to reach the remote microphone. So this is a technique that we use frequently in our work to identify the air acoustic sources. And I'm going to show you a lot of examples today of where we've used this technique to understand blow noise. So the first noise source I'm going to focus on, and what I'm going to focus on most of this talk, is our work on tip clearance noise. And I very much have to acknowledge all the people that have contributed to this work, especially Manoj, who is our postdoc in our group and has really done a phenomenal job with these measurements. So when you have a ducted rotor or a propeller or a fan, there's a very, very small gap at the tip of the blade between the blade tip and the duct itself. And we get very complex vortex structures forming by the flow over the tip and its interaction with the boundary layer that forms on the end wall or the duct wall. And you can see an example of a tip clearance flow here in this sketch. And we have basically quite a few vortex structures. We have cross flow that occurs from the pressure side to the suction side, and that rolls up into this tip leakage vortex. And we also have typically a tip separation vortex here as well, near to the sharp edges of the trailing edge. And that's due to flow separation inside the gap. So we have this complex sort of vortex structure forming in the clearance, in the very small gap between the blade tip and the duct wall. And the sort of the formation of the flow structures in the gap, they're an important function of a whole range of parameters. So the most important one is the gap height, which we call H, but they're also influenced by the incoming boundary layer that forms on the duct wall as well. And the turbulent fluctuations that are produced by these flow phenomena, they interact with the surface of the tip, creating unsteady pressure, which is then radiated to the far field as sound. So that's what we're examining today is tip clearance noise. So the actual noise associated with this flow. And our approach to study tip clearance noise is to use a stationary blade mounted perpendicular to a fixed end wall. And that allows us to study the flow structures and the noise sources in a fixed reference frame. So although this is a rotating blade noise source, we're actually studying it in a fixed reference frame. So I'll start with some of our early work, just to give a bit of context before I dive into our current work. So our early work looked at tip clearance noise from a blade with just a flat tip. And we looked at the influence of a number of important parameters. So the first one was the clearance height. So that's basically the gap height between the blade tip and the end wall, and also the blade angle of attack. And we did this in just a simple, flat, zero pressure gradient end wall turbulent boundary layer. So the first figure here shows the total far field tip clearance sound, or the RMS pressure, as a function of clearance height. So we have clearance height divided by the boundary layer thickness on the x-axis, and then the sound level, overall sound level, on the y-axis. And we're looking at how that changes with increasing angle of attack. So we're going from 0 to 14 degrees. And we can see that, the radiated noise is quite a complicated function of both angle of attack and clearance height. When we're looking at low angles of attack, we have this basic sort of local maximum at about 5 mil, and then just a decay as we increase that clearance further. If we increase the angle of attack further, we start to see this double peak structure here, where we have two local maxima, And then if we increase the angle of attack even further, the double peak structure starts to reduce for larger angles of attack of 12 and 14 degrees. So you can see that the noise is, it doesn't just purely increase with angle of attack, and it changes quite considerably with clearance height as well. And we also performed PIV in the gap to look at the flow structures. So what we're looking at here is the PIV in the small gap between the blade tip and the end wall. And we're looking at the plane parallel to the tip surface and the end wall. And we're looking at the PIV results for two clearance heights. The first one is 2.6 mil, clearance height of 2.6, and then a slightly larger clearance of 5 mil. And in the first column, we have the streamwise mean velocity and then the RMS velocity for a blade angle of 12 degrees. So if we look at the PIV results, we can see we have regions of adverse pressure gradient and favorable pressure gradient in the flow. And we can see the formation of that main tip leakage vortex as well. And near the trailing edge, we can see this jet-like fluid rushing out of the gap and an associated tip separation vortex occurring here. We can see that, as we reduce the clearance height, we get fluid deceleration because we're experiencing, higher blockage. And we can see that the origin of the tip leakage vortex is shifting as well as we change that clearance height. So the origin of the tip leakage vortex is shifting further downstream at larger gap heights. And if we look at the RMS, we can see that there's a lot of unsteadiness or turbulent fluctuations associated with these vortex systems. For the very small gap case of 2.6 mil, we can see some unsteadiness near the leading edge. And then if we reduce the gap from 5 to 2.6 mil, you can see that we reduce the unsteadiness associated with these vortex systems near the trailing edge. So that was our first sort of study, was to look at just a simple tip clearance flow in a zero pressure gradient end wall boundary layer. But in a practical situation where you have a propeller in a duct, the propeller blade is going to be exposed to a range of pressure gradients in the duct. So here we have an example from literature of a pressure coefficient distribution measured on a duct. And we can see that here we have the position of the blade. The pressure gradient begins as favorable, then it becomes adverse ahead of the blade, and then there's a sort of a recovery. And that's the focus of our current work, is to understand what is the fundamental effect of an approaching pressure gradient on tip clearance flow and noise. And we've designed a rig that allows us to grow the boundary layer in different ways and change its properties as it hits the tip gap leading edge. And our focus so far has been adverse pressure gradient effects, but we can also look at favorable pressure gradients too with the rig. So I'll explain the experiment now. This looks rather complicated, so please bear with me. So this is the rig that we've built that allows us to examine the flow structures and the tip clearance noise sources when the tip clearance flow is subject to an end wall pressure gradient. So what we're looking at is the tip clearance flow here. So the flow between the blade tip and this end wall. And we're looking at what happens when we generate an adverse pressure gradient on this end wall. So you can see the rig consists of a blade here that's mounted perpendicular to the end wall. And that leads to a clearance height that we'll, call H between the end wall and the blade tip. And the blade passes through this lower plate, through a turntable where it's mounted to a rotary actuator and a traverse assembly beneath the bottom plate. And we use the traverse system to move the blade up and down and to change the clearance height here. And we use the rotary actuator to change the blade angle of attack. Now, to generate the pressure gradient on the end wall, we do that by changing the inclination angle of the bottom plate. So you can see here the bottom plate is angled to create a ramp, and that either can increase or decrease the cross-sectional area in the stringwise direction to produce either an adverse or favourable pressure gradient on this end wall here. And we also have some side plates installed on the rig too. And these serve the purpose of maintaining the pressure gradient and providing support for the top plate. It's also a little bit difficult to see, but we do have a turntable in the end wall as well up here. And that's got some pressure taps, stringwise line of oriented pressure taps in it. And we can basically change the angle of the turntable to map the pressure on the end wall. So today I'm going to show you results from a gap height between 1.2 mil and 20 mil. So in all cases, the clearance heights that we're looking at are less than the boundary layer thickness. So between 0.05 and 0.85 of the boundary layer thickness on the end wall. And I'm going to focus, we've done measurements at different angles of attack, but I'm going to focus on the 12-degree case today. So to show you a little bit more about the model itself. So here's the blade, and it consists of this main section with a separate tip. So you can see the tip section here. The tip has a flat surface with a rounded edge on it, a rounded edge. So we have pressure taps, if you can see these little dots on the flat surface, as well as on the rounded edge on the suction side of the blade. And there's a bunch of holes at the bottom of the blade that allows us to route pressure tubing through the blade. So from those pressure taps all the way through the blade, out the bottom of the blade, to remote microphones that we place beneath the bottom plate. You can see the position of the taps in this bottom image. So in blue, the blue dots here are the pressure taps on the flat surface, and then in yellow are the pressure taps on the rounded surface. And here's a photograph of the experiment. So you can see the blade. We use a trip to trip the blade boundary layer near the leading edge. We can see in the background a microphone array, which has a foam covering on it. And we use this to measure the far field sound. So it's a 64 microphone phased array placed outside the flow towards the suction side of the blade. So the results I'm going to show you come from the array. So beamforming measurements taken with the acoustic array, and also surface pressure measurements taken with the pressure taps on the blade tip and on the flat surface and on the rounded surface. So first of all, before we put the blade in, we needed to characterize the flow. So we did that using the pressure taps on the end wall without the blade present, so that we measured the mean and the fluctuating pressure on the end wall, first of all. And also we used hot wire anemometry to examine the boundary layer at the leading edge location, but without the blade in place. And we did that for 3 angles of the bottom plate. So 3 ramp angles. The first one is 0 in the sort of grey colour. And that is just a 0 pressure gradient boundary layer. And then we looked at 2 ramp angles of 8 and 16 degrees to generate an adverse pressure gradient on the end wall. So in the first figure, here you can see the mean pressure profile on the end wall. And you can see that varying that plate angle from 0 to 16 degrees changes the pressure profile and the pressure gradient on the end wall. Because we have this sort of open-closed test section, so we have a closed off section and then an open section, which we need, to measure the sound. We have two regions of pressure gradient. We have a strong pressure gradient up to the blade leading edge location, which is marked here, and then a milder pressure gradient where the boundaries are open to the flow. So we can see that we're generating good adverse pressure gradient, a good approach adverse pressure gradient with this ramp at 8 and 16 degrees. And in the bottom row of figures here, we have the boundary layer profiles and the wall pressure spectra that we've measured at the blade leading edge location. So we generate a thicker boundary layer with adverse pressure gradient. We're increasing the boundary layer thickness from about 24 mil in 0 pressure gradient up to 30 mil in the adverse pressure gradient at 16 degrees. You can see in the case of the wall pressure spectra that changing the pressure gradient, so introducing an adverse pressure gradient, affects the low frequency component of the spectrum. The high frequencies remain unaffected. And we calculated the Clauser pressure gradient parameter for the two pressure gradient cases. So for the 8-degree ramp, we're generating a pressure gradient parameter beta of 0.51. And at 16 degrees, we can achieve a pressure gradient parameter of 1.1. So we were fairly happy with the inflows that we're generating on the end wall. So we went ahead and put the blade in and then started our measurements. So here is an example of the beamforming sound maps that we achieve. So this is the measurement that we take with the acoustic array. As I said, it's sort of like a photograph of the sound. So what we're looking at here, if we look at the 0 pressure gradient case, is we can see the top plate and the bottom plate, and then we've also got the blade here. We've got the leading edge marked and then the trailing edge of the blade. And the clearance is just the very small gap between the blade tip and the top end plate. And the color is representing the sound. So where we have the yellow spot, that's where we have the highest sound level being produced by the blade. So we've got 3 results here. We've got the 0 pressure gradient case and then the 2 adverse pressure gradient flows. And you can see the bottom ramp as well in the sound map. So we can see that in all cases, most of the noise is coming from the clearance. We've got this large yellow spot at the trailing edge of the clearance, and that is demonstrating that most of the noise is coming from the clearance itself. In the 0 pressure gradient case, we do have some additional junction noise and trailing edge noise, but the tip clearance is still the dominant noise source. And we can do some processing of these results. We use what's called a deconvolution process to remove the array response from the result. And that allows us to better differentiate between noise sources. So to get better localization of where the noise sources are in the clearance. So this is a map with deconvolution applied, and you can see these individual noise sources in different parts of the clearance. So again, here's our blade, and then here is the top plate. So this is the clearance here, just a small gap between the blade tip and the end wall. And what we do is we divide our clearance into 3 regions: the leading edge, the trailing edge, and then the mid-chord region. And we can integrate these maps over these regions and generate a pressure spectrum, a noise spectrum associated with each region, and then also with the total clearance as well. Okay, so that's what we've done here. I know there's a lot of results on this slide, so I'll try and talk you through what we're looking at. This is our tip clearance noise for a zero pressure gradient configuration. So there's no adverse pressure gradient yet here. The top left shows the total clearance far-field noise spectra for different clearance heights. So we're looking at the level, the sound level versus frequency for the total clearance. So this is all the clearance noise for different heights, different gap heights H. And in general, we see a noise increase with an increase in clearance height across the whole frequency range. It's not linear, there isn't a constant increase with frequency, but there is in general an increase in noise level with clearance height. We can also see at large clearances a sort of broad peak start to emerge. And this is similar to the noise signature that's generated when you have just a free tip vortex forming over a tip of a blade. So now we're going to look at the contribution of noise from different parts of the clearance for 3 specific clearance heights. So we've got clearance height of 1.2, so a very small clearance of only 1 millimeter, 10 millimeters, and then 20 millimeters. And in the black crosses, we have the total clearance noise. And then in the colors, we have the contributions of different regions. So in that red color, we have the leading edge. In the green, we have the trailing edge. And in the blue, we have the contribution of noise from the mid-chord. And what we see is in the very, very small clearance case, we have equal contributions from the leading edge and the trailing edge up until about 5 or 6 kilohertz. And then above that, the leading edge is dominant. We also see a mid-chord contribution in blue here, but that could be some sort of a resonance between the plates. As we increase the clearance to 10 and 20 millimeters, we can see that the leading edge contribution, so the red color, it drops away, and we're left with a strong contribution from the trailing edge in both cases. And this is likely due to the trailing edge interaction of flow unsteadiness associated with those vortex structures near the trailing edge. And then that leads to the noise generation. But interestingly, at 10 millimeters, in blue, we can also see a significant high frequency contribution above 4 kilohertz from the mid-chord. So to summarize, small clearances, we have equal contribution from the leading and trailing edge. As we increase the clearance, we see, trailing edge noise being dominant, but we also have a mid-chord contribution at these sort of 10 mil clearance heights. So the clearance height has a really strong impact on where the noise sources are within the clearance. So now we're going to look at what happens when we introduce adverse pressure gradient. So now we're looking at the total noise measurement from the clearance in both zero pressure gradient and adverse pressure gradient conditions. So in the grey is the zero pressure gradient case, and then the red and the blue are the different pressure gradients. And we're looking at the result for a small clearance height of 1 mil, 5 mil, and then increasing it to 10 and 20 mil. So we can see here that the clearance has a pretty subtle but important change in noise level with pressure gradient. So just to keep in mind that it might not look like much, but in terms of decibels, we're measuring the sound level in decibels. So a 3 dB change is something that is perceptible. 5 dB is, really clearly noticeable change. And then if you're changing something by 10 decibels, it's either half or twice as loud. So even though the changes look small, they are still, significant in a decibel scale. So the frequency range of the pressure gradient influence, we can see it increases with clearance height. So at 1 mil, we're only getting a sort of a reduction in noise level with pressure gradient, with adverse pressure gradient above about 6 kilohertz. But then if we go to a 10 mil clearance, you can see the pressure gradient, the adverse pressure gradient reduces the noise levels above about 3 kilohertz. And then larger clearances show the largest effect of pressure gradient. The adverse pressure gradient reduces the noise levels below and above this sort of peak here. So we are seeing sort of small but important changes with pressure gradient by introducing that adverse pressure gradient to the end wall. So now we're going to start investigating sort of what we're seeing and why we're seeing it. So I'm going to move now to looking at the pressure spectra. So these are the measurements, the fluctuating pressure measurements taken on the blade tip. So there's a lot of information here. And again, I'm going to try and highlight the most important things to look at. So here is our tip. So we're looking at the pressure measurements in blue along those taps on the flat surface, and then in yellow, those taps on the rounded surface. And the top two figures show the RMS pressure fluctuations along the cord. So this is on the flat surface and the blue taps, and then this is on the rounded surface, the yellow taps. So this is RMS level versus cord position. And we're looking now at the zero pressure gradient case and how the pressure fluctuations change with clearance height. And then the two rows of figures below are looking at the specific spectra, the pressure spectra, with all clearance heights at these locations that I've circled in red. And they're also highlighted by these red boxes in the RMS plots too. So if we look at the flat tip now, at very small clearances in the red and blue, we can see that the fluctuations are pretty constant all along the flat tip, and they're fairly low except at the leading edge and the trailing edge where they increase. As we increase the clearance height, we see this large jump in the pressure fluctuations at a clearance height of 8 and 10 mil. So in the yellow and the dark blue. If we increase the clearance height to 8 and 10 mil, we see a really large increase in the mid-cord in these pressure fluctuations. And correspondingly, we see this in the spectra. So this is the pressure spectra at the middle cord position here on the flat tip. And you can see that the yellow and the blue are really high amplitude. You know, the pressure levels are highest at these two gap heights at the mid-cord. And this aligns with the far-field noise results where we saw a strong high-frequency noise source from the mid-cord at these particular gap heights. And we attribute this to the crossflow. Essentially, you know, as we open the gap up, we get this intense jet of crossflow over the surface of the tip at the mid-cord that leads to these high fluctuating pressure levels at these gap heights. On the rounded surface, we can see, if we look at the RMS, we have large RMS values at small clearances, so the red and the blue. Correspondingly, if we look at the spectra at the leading edge, so this one here at the rounded surface, we see the red and the blue are high across the whole frequency range. So we're getting high energy levels on the rounded surface for very small clearances. And then we get a crossover point where we see at the trailing edge, the fluctuation levels increase with clearance height. And now we thought, okay, you know, let's have a little bit of a think about why that's happening. So we performed just a RAN simulation for a small gap height of 2 millimeters. So we're looking at the small gap case. And in this case, if you remember, we saw that the noise comes from both the leading edge and the trailing edge. And we also saw high amplitude pressure fluctuations at the leading edge on the rounded surface. If we look at the simulation, so we've got here the streamlines and then the wall pressure on the blade, and then the Lambert 2 vortex visualization as well for this small gap case. So what we can see that for very, very small gaps is that we have crossover flow occurring over, most of the chord length here. And we can see if we look at the vortex visualization that the origin of the main tip leakage vortex is quite far upstream. And we also have a secondary vortex too here that's paired with that tip leakage vortex. And that forms on the rounded surface. So it's possible that when we have this very small gap height, and then these vortex structures are located very close to the leading edge, it's the flow unsteadiness associated with these phenomena that interacts with the leading edge to create that unsteady wall pressure that we see and the strong contribution of leading edge noise in the small gap case. As the gap opens up, this tip leakage vortex, it shifts downstream, further along the blade, and this secondary vortex disappears. And that's when we have that strong cross flow over the mid-chord, leading to a mid-chord noise source. And then we can look at how the pressure fluctuations are impacted by the adverse pressure gradient. So similar to the other figures, we have the RMS pressure along the chord on the flat surface for the three pressure gradients and 3 gap heights, and then on the rounded surface. And then I've got selected spectra down here at the tap locations that are highlighted by the red boxes on the flat and rounded surface. So what we can see is that the pressure gradient effects on the wall pressure really depend on which region of the flow we're looking at. And I'll highlight just a few of the key features. So pressure gradient has the most effect on the gap height of about 8 to 10 mil, especially on the flat surface at the mid-chord. So we can see here on the flat surface at the mid-chord that we get a strong reduction in the surface pressure levels with adverse pressure gradient. And this is corresponding to where we see some reduction in the far field noise at these gap heights with adverse pressure gradient. On the rounded surface, we see a difference in the trailing edge levels. So adverse pressure gradient leads to lower fluctuating pressure levels on the rounded surface in the trailing edge region. So we're looking at the pressure spectra at this red tap here, down here at 3 different gap heights and the 3 pressure gradients. And we see that we get lower spectral levels in all cases in this trailing edge region with an adverse pressure gradient. So that was a lot of information to take in. I know that's a really complicated flow and there's a lot going on. So I just want to summarize our findings so far on this topic. And that's to say that at the small clearances, the leading edge and the trailing edge clearance noise contributions are comparable, up to about 5 or 6 kilohertz, above which the leading edge is the dominant noise source. And as the gap increases, the trailing edge clearance noise becomes dominant, but we also see this high frequency noise contribution from the mid-chord at specific gap heights of 8 and 10 mil. On the flat tip surface, we have high amplitude pressure fluctuations at the mid-chord for those gap heights of 8 and 10 mil. And this corresponds to that acoustic source, likely associated with the strong crossflow in the mid-chord region. On the rounded surface, we have high amplitude pressure fluctuations at the leading edge for very, very small gap heights. And this is where the leading edge clearance is a dominant noise source. And this coincides with the tip leakage vortex forming very near to the leading edge, and it also pairing with a secondary upstream vortex. And we saw that adverse pressure gradient effects on noise are really important but subtle, and they're most obvious at large clearance heights. The adverse pressure gradient reduces the high frequency noise, and the reduction extends to lower frequencies as you increase the gap height. The most pronounced effect is on the sort of mid-chord region in terms of the surface pressure for the 8 and 10 mil gap. And this corresponds to when we see the mid-chord being an important noise source. So this indicates that the adverse pressure gradient influences that cross flow, so the strength and the location of the cross flow over the tip. So that's all I've got to say in terms of the tip clearance noise. I did have a little bit more, but I can see we're getting really short on time. So Azadar, would you like me to continue, or should I wrap up there?
This is up to you if you would like to present a few more.
Okay, I'll keep going for a few more slides then. That's great. So something I would like to share with you before I finish is just some of our latest work looking at measuring the fluctuating surface pressure actually on the blades, the rotating blades of small rotors. So I'll definitely like to acknowledge Justin here. Justin is a PhD student in our group who is leading this work and doing a terrific job. So this is the rig that he's developed to look at the fluctuating surface pressure on the blade with relevance to, small unmanned aerial systems, UAVs or drones that are used a lot in commercial and defense applications. And as their use becomes more widespread, the noise they generate is really, becoming problematic. So we're interested in understanding what are the sources of noise on these small rotor blades. These blades produce tonal noise due to their revolution and also broadband noise. So a major source of the tonal noise is the steady aerodynamic loading on the moving blade, relative to someone who is stationary, say on the ground. And then we have broadband noise being produced due to turbulence interacting with different parts of the blade. So to help us understand noise generation from rotating blades, this new rig has been designed to measure the surface pressure on these blades here. So we use 3D printed blades, and we use this remote microphone method again. So we're measuring the blades using microphones here that are integrated into the rotor's rotating reference frame. So there's this cylindrical 3D printed hub of 6 microphones that connects to pressure taps on the blade surface. And then at the bottom end of this rig, we have a slip ring that allows us, allows this electrical connection between the rotating microphones and the external data acquisition system. And you can see the motor that drives the system here, and then we also have a torque and thrust load cell too. So here's a look at the experiment. So we're trying to understand, what is the noise that is radiated by these small rotor blades, and what are the actual sources of noise, that are responsible for the noise signature. So here's the experiment in our anechoic wind tunnel. You can see the rig here, and it's enlarged in this photo here. So we've got a foam-lined aerodynamic shell over the body of the rig. Here are the 3D printed blades, and then the nose cone. And we've got, to measure the far-field sound, or the radiated noise, we have arc arrays around the blades. And then we're measuring the fluctuating surface pressure on the blades themselves using pressure taps. And Justin's created a series of different blades, pressure taps in different locations. But the ones that are shown here have matching pressure taps on the suction and pressure sides at various positions along the cord. And you can see the hollow channels that run through the blade, and we connect those to plastic tubing and then to the remote microphones. So this is some of our very first results. I'm really excited to share them with you. This is really proof of concept at this stage to see whether we can actually measure the aerodynamic noise with this technique on blades that are rotating. So what we have here is the spectra that is measured with one pressure tap on the suction side in a static condition, so no flow at 0 meters per second, and then with flow at 10 and 15 meters per second. And the solid lines are with the ports just open and measuring signal, and then the dashed lines are when we cover the ports with tape. And we're looking at the pressure spectral level versus BPF. So BPF is the blade passing frequency. It's twice the frequency of the shaft rate because the propeller's two-bladed and we've got two blade passes occurring within one rotation cycle. So we can see we've got these really strong tones with the ports open and also with the ports closed. So we can see that in all cases we're measuring these strong tones. And we can also see a broadband level that increases, so this broadband level increases as we increase the flow speed. So we expect tones in a free stream flow, so when the flow is at 10 or 15 meters per second, because the blade motion into and out of the free stream is cyclic, leading to these tones associated with the aerodynamic loading. We can also see some tones though in the no flow condition, so 0 meters per second in red and with the ports blocked. This might be because we're seeing the result of some vibration perhaps that's causing the blade to flap. However, the fact that we're getting an increase in the tones with a free stream velocity is really encouraging. And it suggests that the cyclic loading is higher than the loading due to the vibration of the system. And we've also got really high coherence here. So this is for the free stream velocity of 15 meters per second. We're looking at the coherence between the signal measured at the port on the pressure side and on the suction side. So the coherence between the corresponding ports on the two sides of the blades. And we can see we've got, good high coherence at BPF and harmonics. And this tells us or indicates that the transducer is picking up a strong aerodynamic source signal. So these results are really encouraging. We can also use some data processing techniques to isolate and remove the tonal components just to examine the broadband signal as well. So there's lots we can do with this, and we're really excited to use this rig to explore the noise sources on rotating blades further in the future. Okay, so I think that's all I'll say, except I would certainly like to acknowledge and thank everyone in the Flow Noise group for, all their contributions to this body of work. And here's a great photo of us at the last AFMC. So yeah, thank you very much. And please feel free to reach out anytime if you, would like to speak to us about our work, or if you've got any, further questions after today, I'd be more than happy to speak with you.
Well, thank you so much, Danielle, for a very interesting and nice talk. I think we all enjoyed it a lot. So if anyone has questions, please feel free to either speak up or type in the chat. While we are waiting, I will ask one thing about the pressure gradient effect that you mentioned. And you said adverse, but you mentioned you could potentially look at favorable. Are you interested in looking at favorable pressure gradient in terms of how applicable that would be to the types of, in the application? And do you expect it would have a similar effect?
Yeah, that's a really good question. I think, yeah, right now our work is, it's very fundamental. It's looking at the effect of pressure gradient on these clearance noise sources from a very fundamental point of view. And we have only looked at an adverse pressure gradient, but in a duct, you do have a favorable pressure gradient ahead of the blade too. So absolutely, we would be interested in trying to understand the favorable pressure gradient effects. How would it change things? Well, the boundary layer would probably be a lot thinner. So it may, yeah, I'm not exactly sure what exactly it would do, how significantly it would change things. The boundary layer would be thinner in that case, and maybe it would allow some of those vortex structures to be enhanced. That's what we've seen in the case of just a shedding from a cylinder. We get, you know, stronger tonal noise and stronger vortex structures in a favorable pressure gradient. So maybe that would happen in this case as well. But yeah, that remains to be seen, and certainly something that we could look at for sure.
Yep, thanks. Do we have any questions from the audience? A comment?
Yeah, feel free to share comments, or if you've got any ideas as well of what's going on or how we could improve, I'm more than happy to hear those.
We have another comment from Bart Kenyon, who says, thanks so much, Danielle. Really clear presentation. I appreciate you sharing early data. The slip ring rotating test rig looks awesome.
Oh, great. Thank you. Great. Really appreciate that feedback. Yeah, it's pretty exciting. Both of these experiments are really complicated and, you know, really take a lot of work from the team. So yeah, it's really great. I look forward to seeing, you know, what we learn from all of this work moving forward. Oh, Pat, you've got a question?
Yeah, would you like to ask a question?
Hi, Pat.
Hey, Danielle.
Nice to see
Fantastic
you.
presentation. Yeah, nice to see you too. I have a question. So far, your testing has been like 6 degrees, I believe. Have you thought about doing any other incidences at the moment?
Yeah, we so most of the results I showed was at 12 degrees.
Sorry,
we have 12. Yeah, no, that's fine. We have looked at our earlier work, we looked at sort of 0 to 14 degrees, and we looked at really fine angle of attack changes and how that changed the noise from just a square flat tip. In this body of work, when we're introducing pressure gradient as well, we've cut it back to just 3 angles of attack. So we have done the 0 angle of attack case, 6 and 12 degrees. Those are the ones that we've been focusing on. The flow structures are definitely more enhanced, more well-defined. The noise signature is stronger from the 12 degrees case, which is why we've focused on that for sort of more detailed investigation. But for this blade, we have looked at 0 and 6 as well.
Yeah, awesome. Yeah, it's fantastic work. I really like the 3D printed blade that you could see all the pitot holes or the tapping.
Yeah.
That was beautiful. Yeah.
Oh, thank you.
Any other questions? Yes, then, well, thank you, Danielle, for the talk. I mean, we already enjoyed it, and we look forward to seeing more of your results.
Oh, thank you. Yeah, thanks very much for having me. And yeah, I hope we can share more, you know, the next AFMC, I guess. Fantastic.
Yeah.
Thank you very much.
Thanks, everyone, for joining.